Okay, so I guess we are live now. Let me close this tab so I don't have feedback. So welcome back to our deliberations on NIM variants. You might see, if you're watching the recordings, you might see a bit of a jump discontinuity in the playlist, and that's because the date and recording for some technical reason is not available. And that's when we discussed Fibonacci NIM. And it was a meandering discussion that did not get anywhere. And today is going to be more of the same. But let me just back up a bit and remind you about the rules of the game so that we can talk about it more. So in Fibonacci NIM, unlike NIM, we play only with a single pile, which is something that I may have misrepresented when I first introduced it. So you're welcome to think about variations that have multiple heaps or multiple piles of tokens, but we're going to stick to the traditional Fibonacci NIM variant, which just has one heap of n tokens. And in fact, a good way of describing a state of Fibonacci NIM would actually be the number of tokens on this heap plus a budget for how many tokens can be removed in the current move. So I'm going to denote that budget by B, right? And the rules are that to begin with, the budget is always going to be n minus 1. So we have in some sense, a starting budget of n minus 1. And on subsequent moves, the budget is 2 times the number of tokens that were removed in the previous move by the opposite player, right? And the reason I want to think about the state of Fibonacci NIM as a pair n comma b is because if you think of it only in terms of n, then it can be a little bit misleading, especially when you want to apply inductive arguments. And maybe let me give you an example of what was tripping me up when I was thinking about it. So, for instance, what we said was, okay, let me also, before diving into this, recall that something that we will use when defining the winning strategies is the so-called Zeckendorf representation of a number, which is a unique way to represent a number as a sum of non-consecutive Fibonacci numbers. So let me actually describe a quick proof of the fact that the Zeckendorf representation exists and it makes sense. So we want to say that every number n can be written uniquely as a sum of non-consecutive Fibonacci numbers. And for the Fibonacci numbers themselves, this unique representation comes from the number itself. There's nothing more to be done. So if n is itself Fibonacci, then n can be just written as, this looks funny, but it's just the sum n. So it's going to be maybe slightly more meaningful way of writing it is that n is fi, which is like if it's the ith Fibonacci number, then it can be written as basically itself. Of course, f of I by definition is also f of I minus 1 plus f of I minus 2 and so on. And you could expand these out further, but notice that you'll never be able to shake off the consecutiveness of the numbers that show up in these alternate representations. So writing a number as a sum of Fibonacci numbers themselves without the constraint of them being non-consecutive is not necessarily unique. But once you impose that you can only use non-consecutive numbers, it turns out that it will be unique. So let's check out what happens when n is not Fibonacci. Well, in that case, n is sandwiched between some two consecutive Fibonacci numbers, let's say fi minus 1 and f5, right? You just move up the number line and look for the last Fibonacci number that n is greater than. That would mean that it's smaller than the next one. And so this is a well-defined place to position n at. And now a natural way of writing n as a sum of non-consecutive Fibonacci numbers is to basically say, well, n is f of I minus 1 plus whatever that gap is between n and fi minus 1, right? So let me denote this gap by a. So you can see that this is fi minus 1 plus a. Of course, there's no reason to believe that this gap itself should be Fibonacci, and indeed it may not be. But notice that a is strictly less than n. So at this point, you can appeal to the induction hypothesis to write this down itself as a sum of non-consecutive Fibonacci numbers. Now, you might be worried about a having, for example, fi minus 1 or fi minus 2 showing up here. And we want to argue that that's something that will not happen. So that's something that I'm not going to delve deeper into in the interest of time, but this is essentially the idea of pulling up a Zeckendorf representation. You can also do it there are like at least two other ways of doing it. One is to say that you start off writing n as a sum of n ones. And you can think of the ones as being, for example, the 0th and the first Fibonacci number. And in general, you keep applying this principle, which is that as long as you see two consecutive Fibonacci numbers, you mash them into the next one. So in some sense, you get rid of the issue of consecutiveness. So I think that's one approach that we took last time. And the other one that turns out can be shown to be correct is that you follow a more greedy approach, which is a translation. It's sort of an algorithmic version of this proof, if you think about it. So the greedy algorithm to generate a Zeckendorf representation is simply the following. Look at the largest Fibonacci number that fits, that's smaller than the number that you're working with, whose Zeckendorf representation you want to find. And you throw that number into your basket of the things that are going into the sum. So take the largest number that fits, and now look at what remains and repeat. So that's essentially this inductive step here turned into an algorithm. And the proof that this inductive representation of A, the inductively obtained representation of A, does not clash with fi minus 1 in terms of producing consecutive numbers. That's kind of what is going to be key to the correctness of the greedy algorithm, right? Okay, so those are some thoughts, slightly incomplete, but I think very doable as sort of food for thought kind of exercises if you want to convince yourself that the Zeckendorf representation exists and that it's unique. So the uniqueness has to be explicitly established, but it's not hard to do. So I will skip over the details there and move on to why all of this is relevant to Fibonacci nim. So coming back to the analysis of Fibonacci nim. So if we only treat the states of the game as these numbers, here is where it can sort of get confusing. So roughly speaking, the claim is that the P states, that is the other player wins, correspond to Fibonacci numbers. And the reason I find this confusing is because notice that a P state is only supposed to have n children, right? because you want to say, well, whoever is playing at this state is going to lose, because no matter where they go, they're going to throw the game away to the opponent player. So that's kind of at the heart of how we analyze any of these game trees. Whereas for an end state, it's enough to find a p child. Now, when we are saying that the p states correspond to the Fibonacci number, I really mean that these are the only p states in Fibonacci NIM. That's at least the claim. And where this can get confusing is, well, suppose you have a Fibonacci number fi, which can be thought of as fi minus 1 plus fi minus 2. Well, it's conceivable that you have enough of a budget to get rid of just fi minus 1, for example, which will leave you with fi minus 2, or the other way around. You could play by removing fi minus 2 tokens to be left with fi minus 1 tokens. Either way, the point is that you are at a p state and you have made a move into what is apparently another p state, right? You have removed a certain number of tokens that again leaves you with a Fibonacci number of tokens. And if that's a valid child starting from fi, going down to fi minus 1, for instance, then it's really not clear, how this works out, because fi minus 1 is, at least according to our own claim, a p state, but that violates just like how p states behave. And I think the reason this is happening is because we're not truly accounting for the budgets that are involved. And that I think the way we want to characterize the P and the N states should be a little more nuanced and should certainly take the budget into account. Because if you just look at the number, then that's an incomplete representation of the game state. So I hope that that sort of makes sense. So we're going to actually denote a state of Fibonacci NIM as N comma B, where this is the number of tokens. N is the number of tokens and B is the budget for how many tokens you can remove. So certainly if you are at a point where you have N tokens and a budget which is at least N, then these are the trivial N states. Because whoever has such a state is able to remove all the tokens immediately and you are done, right? On the other hand, I guess one quick observation, although this may not tie in immediately to the winning strategy, but I think it's a helpful way of thinking about the game when you're playing it, is that if you have N tokens, certainly not advisable to remove more than 1/3 of them at any stage. Okay. So even if you have the budget for it, if you remove more than 1/3 of the tokens, then the number of tokens that remain will be within the budget of the next move, right? So if you start out with N and a budget B, and you go to N minus M with a budget B being 2 times M, and M is greater than 1/3 of N, just to be on the safe side, maybe let me throw a ceiling in here. Well, that means that, well, what you're left with is at most 2/3 of N. And the budget is 2 times 1/3. So you basically give people enough room to eliminate all the tokens, right? So you're basically moving into this kind of a state when you remove more than 1/3 of the tokens. So in case you happen to be playing Fibonacci NIM, but somebody, then make sure to not remove so many tokens that you give the other player an immediate free hand to finish off the game. This would be like a 2-round Fibonacci NIM game and not so interesting. So that's just some intuition for what not to do in your first move. On the other hand, let's talk about how the second row of representation comes into play when you want to actually devise a winning strategy. Okay, so here are two related claims. So let me write down n as sum of non-consecutive Fibonacci numbers. Let's identify this, the smallest one. Okay. And I want to denote this by T of n. Call this the tail of n. It's just the smallest Fibonacci number in the second row of representation of n. And now I want to say that if you have a position n comma b, where the budget b is smaller than T of n, that means that, in other words, the current player cannot afford to remove the tail. So that's what it means to be in this situation with respect to the budget. So what we are saying is that if you don't have enough of a free hand to remove the tail, then that is a losing position. Okay. And that's the claim. But notice that if you believe this claim for a moment, then anywhere else where B is at least the tail is going to be winning. And the reason for this is simply that Fi2 here, which is the next number, the next Fibonacci number after Fi1 in the second row of representation. So notice that I2 is strictly bigger than I1 plus 1 because of the non-consecutiveness, which means that you've hopped over another Fibonacci number to get to Fi2. So whenever your budget is at least the tail, right? And I'm talking about numbers that are not themselves Fibonacci, all right? So I should have prefaced that when I said otherwise it's winning. I'm talking about numbers that can be actually broken down non-trivially into a sum of non-consecutive Fibonacci numbers. If it's itself Fibonacci, then what I'm going to say will not apply, right? So you have at least two numbers in the second row of representation, and your budget allows you to remove the tail. In this case, you should just go ahead and remove the tail. What happens is then you transition from n comma b to n minus T of n from our budget, which is 2 times T of n. And if you think about what the second row of representation for n minus T of n should be, well, it's just going to be what remains after the tail is removed. Okay. And because Fi2 is going to be larger than 2 times Fi1, right? This again is a property of Fibonacci, right? So because this is true, and this you can, I mean, this is, of course, intuitively, hopefully a reasonable claim to make because you are, the Fibonacci numbers roughly double at every step and you've skipped a step. They don't quite double, little less than double, because you are adding on a previous Fibonacci number to the current one to obtain the next one. But once you have skipped over one, then you have certainly more than doubled from your current position. And one way to do that is to just plug in the recurrence, use induction, and so on. So that's going to be a fairly standard inequality here. In fact, there might also be a nice way of even visualizing this. So if you come up with something that's kind of very transparent visually, then please let me know. But in any case, the point is that once you make this particular move, then you are exactly in the sort of positions that we identified down here as losing. Because of this inequality, the current budget here does not allow you to remove the tail, right? So this really is sort of at the heart of the second rough based argument for Fibonacci nim. But for as long as n can be written as a sum of more than one non-consecutive Fibonacci numbers, then get rid of the tail to go to a position where the other player cannot afford to remove the tail. And then there is this sort of back and forth where whatever the other player does, you come back to a situation where you can afford to remove the tail again, and you keep going accordingly, right? So there are a couple of claims that I will write down explicitly without proof, which will kind of account for the correctness of what we are saying here. So what we want to say is that if the budget is smaller than the tail, then sorry, I think I got that mixed up. I want to say that this is a winning position. This is what I said earlier. So if we have the other player remove anything that falls short of the tail, right? Then we're left with something that's good for us. So if what is being removed from n is smaller than the tail of n, then the position that we will be left with is going to be a winning position. And this involves, in some sense, staring at what happens when you get rid of b from n. What does the second row representation of this new number look like? And in particular, it also involves understanding that the representation of b does not involve a certain Fibonacci number. So this does require an argument. And again, I'm not going to dive deeper into this, but since all of us are on the group, I'm going to share a document which does actually go over all the steps involved in making this claim. So here what we are saying is removing a number of tokens that falls short of the tail leads to a winning position. So these are essentially scenarios from where, like, basically no matter what you do, you're going to have the other player win. Okay, so here actually maybe I'm overloading a little bit. I hope this is not confusing. So maybe let me just use P here. to say that P is the number of tokens that we remove. So then that's the budget that we end up with is 2P. And so basically, if you can create a situation where the budget is less than Tn, then you're in good shape, because all the moves that are available from such a position are going to be winning for the player who is in that new position. On the other hand, this basically directly implies this claim that n minus p with a budget of 2p is a losing position if p is the tail of n. So this is basically saying that whenever you can remove the tail, if you do remove it, you go into a losing position. And that's because that's exactly the sort of position that we analyzed here. Because when you have a budget of 2p on n minus p, what we said previously is that this budget will not allow you to remove the whole tail, right? Because you're stuck with the tail being fi2, which is bigger than 2 times fi1, which is what we are removing when we say that p is t of n, okay? So this basically is morally, in fact, literally equivalent to saying that we have removed fi1. So this budget here is going to be smaller than 2 times fi2, which is the tail of n minus p. And then you appeal to this here, right? So once you have convinced yourself that when the tail is not affordable to remove, then you have a losing position, then the fact that you can get there is just a property of how Fibonacci numbers work. This may not be the only winning strategy. There could be situations where you can remove a longer tail and still get away with it. But there's a question of how far can you go, because once you've started removing too much, then you give the other player enough leeway to get rid of everything. So you don't want to play dangerously. So this is one winning strategy that definitely works, but you could ask yourself if there are others. I'm also generally curious about the length of average gameplay. How long do these games go? If you're playing the winning strategy, you're consistently only removing tails, it seems to have sort of a log vibe to it, because you seem to be, well, I'm not even sure if log is the right thing to say here, but I suppose what I do want to say is that the first player is going to push the game to as many rounds as there are numbers in the second row of representation, although the second row of representation is going to change as we go along, depending on how the opponent player makes their moves. So you could, it's not even clear that it's a monovariant, that the number of terms reduce or do not increase. None of this is kind of completely clear, actually. And of course, if you're talking variations, then what happens when you introduce more than one pile is also interesting. And there it's not even unambiguous how you extend the rule set, because you could either generalize this rule set in a natural way, saying that the game just begins as normal game does. You cannot empty out everything. And now if there's more than one heap, since you're constrained to playing in a single heap, you cannot empty everything anyway. So there's nothing to be said in the first move. But all the current moves determine the budget for the next ones. Or alternately, and this was a suggestion that came from Akash before we started the recording, what you could say is that every heap maintains its own sort of private budget counter, which begins as the size of heap -1, which means that in the first move, you can't even empty out one of the input heaps. And then as the game progresses, depending on where the move was made, it's that heap's budget that gets independently updated. So I think that's sort of certainly a different game from the one I first described. And I feel like both of these variations would be interesting to look at. I believe some of it has been looked at in the literature. Some of the multi-heap Fibonacci NIM results are around trying to identify what sort of Grundy numbers or numbers you associate with different states. But I think not everything is fully settled in terms of who wins and things like that. So I'm not 100% sure about the literature on generalized Fibonacci NIM. And in fact, even finding a reasonable explanation for the winning strategy here for the single heap version was admittedly not completely trivial. So I do have one or two references which I thought were quite nice. In the book, I believe it's largely left as an exercise with the main intuition being provided in terms of remove the tail. That's the strategy. But since the budget is not introduced as an explicit aspect of the game state, I think the notation can get a little confusing, especially when you apply induction, which is what I was trying to give you a heads up against right at the start here. So this is something I'd watch out for if you're going to think about this a little bit offline. Just make sure to think of Fibonacci in terms of a number and an associated budget or a quota. That's the term used on the Wikipedia page for the game. And I certainly do mean to try and write up a clean proof for both of these claims that we are making here. And I will try to share that soon. But in the meantime, I think there is a nice paper which does describe this and also goes beyond and analyzes this game quite a bit further. So if you're interested, do take a look at that. But that said, I think we're on time. So I will call this a wrap here, at least as far as the recording goes. And we'll continue tomorrow with yet another NIM variant, and that will be the concluding discussion for this aspect of games where we're looking at impartial games, normal play, and then the next thing after that will be a game called Geography, which is a game which is actually played, I think. It's one of those things that has an Antakshari vibe to it. You give names of places, and I start with a name, and you're supposed to revert or continue the game with another name that begins where using the same letter where my name ends, and so on and so forth. And that's something that you can formalize as fun game on a graph situation. And that's something that we will look at once we have dealt with one more NIM variant, which is, like I said, the topic that we will focus on tomorrow. So that's sort of the limited roadmap on what's coming up. So we'll continue this tomorrow. Thanks so much. Bye for now.